All yours.
Thanks, Antonio, and thanks, Gary, for your kind invitation. And welcome, everyone. I hope if you have any questions, feel free to interrupt at any moment. But of course, I'll be happy to take questions after the talk as well. It's always nice to start. Let me see if I can get rid of those messages here on the screen, because I'm sharing my entire screen. Might be getting in the way. Maybe that's all right for now. It's always good to get a sense of the size of our solar system, and in particular, the object we will be dealing with in this talk. And this is a star, it's the sun. And here, I want you to try to get a sense just by looking at an object that you already know. Well, of course, the Earth, we live on the Earth, but one could argue that the Earth is a planet we cannot really see unless we look at satellite pictures or whatever. So I put here the moon in as close to scale as possible. So you can see that it takes about 4 moons, placing it, cycling in this kind of way, cover the diameter of our planet. And that gives you an idea of the scales involved here. So we start from that. Now, another interesting thing to keep in mind is that the moon is quite far away. And in the next slide, I'll show you it takes about 30 times the size of a planet to cover that distance between the moon and the Earth. And yes, indeed, I copied and pasted exactly the same image by hand. I may have played some tricks, but anyway, you get the point. Now that we understand the scales from our neighborhood, let's see when we have a comparison to the sun. Here's the sun, here's the Earth. If another metaphor or analogy might serve you better, you can think of a basketball. And the Earth, if the sun is the size of a basketball, the Earth would be about 1/16 of an inch. And the moon will be a fraction of that. That's a good idea. Now, some of you might already have noticed there are some blemishes on the sun, so those are called sunspots, and you can see that approximately they are roughly as big as our planet, but they are flat areas on the surface of the sun. We'll try to cover that in a moment. And now that's the size of the sun, but let's understand a bit the distance between the Earth, which is right there, and the sun, which is right here. The size is now not to scale, but the distances are to scale. It takes about 100 suns, not 100 Earths, 100 suns to cover that distance. It's pretty amazing if you think about it. So, in summary, sort of that helps you build a measuring stick, so to speak, so you can understand what you will be seeing in this presentation. Put a bit of an effort to cover the history of things, as I promised in my title talk. But considering that this might get a bit too technical, I might take the liberty and skip some slides every now and then to adjust it to what you guys are more interested. But at any rate, that's really the summary of the scales and the sizes of the structures we are going to be looking at. Antonio already pointed out that the sun has been an object of worship since the beginning of humankind, or at least any information we have in recent history. Here you can show different cultures: Mesopotamia, Egyptian, Central European, Greek, Roman, Aztec here in the Americas, Hindu, and from Japan. I'm sure there are many, many others, just a collection, just to see that each of these cultures consider the sun a life giver. And it truly is. Without the sun, probably wouldn't be here. All right, another thing that really triggered a sense of wonder or even fear to those early humans were the solar eclipses. And here you can see a picture of a solar eclipse that was taken back in I believe that was 1999. And you see some features of interest here. You see the extended tenuous atmosphere of the sun, this kind of diffuse white glow, together with some red flames. Now, the red flames have been first mentioned during an eclipse that was observed about 1,000 years ago in the Laurentian Codex, which is a Russian collection of chronicles. Some wealthy aristocrat had the money to pay somebody to collect information about those times. and they compiled in the codex. So they discuss the appearance of red flames when an eclipse happened in Europe, and trying to get an understanding of what these are. But you can imagine what this site might have triggered, to the people, to those humans across history that didn't really know anything about our star. So out of nowhere, while they were living their lives with all the hardships of those different times that they lived compared to our times, on top of that, they had to suffer the sudden, vanishing of our own star. So imagine the horror, the terror that was in this cost, including those red flames. Look pretty scary if you happen to have seen these eclipses. It's actually a movie, but maybe not sure if it will play. Oh, it actually plays. So it's a movie I recorded myself with my phone from Dallas, Texas, a couple of years ago. And that's pretty much how it looks in the eye. Our phone cameras are actually doing a better job than our eyes do. I was even able to zoom in. And if the sound was playing on this video, you could hear all the people gasping, like they couldn't really believe what we were saying. In Dallas, Texas, not 1,000 years ago. So, all right. So the main point to take here is that since the sun was an object of worship, was considered to be a perfect celestial object, whatever that meant to any culture. No blemishes, no imperfections. However, back in, again, the 12th century, in particular, Sunday, December 8th, 1128, another chronicler, or actually a monk, in the area of Worcester in England, noticed two big blemishes on the sun just by looking through the fog in England. And he actually took a note. If any of you knows Latin, maybe you have read what this says. Of course, I'm joking, and it's really convoluted writing here, the old scripture. But the idea is that this chronicler is actually explaining what he saw. And on top of that, he put the effort to make a drawing, which is pretty amazing. And you can see in the Sanskrit that he describes it as a large spot on the sun, on the upper end of the sun, whatever he was calling it. I don't think it's called it north or whatever. And another smaller sunspot on the star. And I think he said that a few days later, they disappeared. So that was taken as a bad omen. One can imagine. Now, that was 1,000 years ago. Let's go a bit closer to our times, and that's not too close to our time, still about 400 or so years ago. Thomas Harriot in England, back in 1610, was the first one who actually took recordings of sites of sunspots on the sun. Those are actual hand drawings. And as you probably know, most, or any of you have heard in the past, it was Galileo who was the first one. Turns out it wasn't. We know for sure now it was Thomas Harriot. Sadly, Thomas Harriot died on the same year, I believe a few days after he made this drawing, while Galileo managed to live longer. Of course, he had other problems with being persecuted for his scientific views, for clashing paradigm of religion at that time. However, he did leave recordings of his views of the sunspots. And actually, give me a second, I have a movie, kind of a flip book movie, because Galileo took recordings. That's actually wrong, I think it's 1612. Yeah, it's right here, 1613. On June 1613, Galileo took the effort, and every day took the effort to record the position of sunspots. And he didn't have the means at that time to play a movie, but I do.
Oh, wow.
You can actually see what he managed to see himself by observing the sun. The only person that he was aware of, didn't know Thomas Harriot, was another contemporary of his, but he lived more than 1,000 miles away from him in England. Galileo was in Italy. So anyway, that was really an indication to Galileo that the sun not only has blemishes that appear and disappear, but it also seems to be rotating around itself. Please, yes.
So how did he do this? Did he project it on something? He wasn't looking directly, right?
Excellent question, yes.
Okay.
That's a technical question, but an excellent question. Indeed, he did not try to look through a telescope.
Yeah.
We know that Thomas Harriot tried to look through a telescope, which is terrible. But he tried to do that at the time he felt it was more comfortable. It was actually really early in the morning, where the sun was really on the horizon and the intensity was a bit attenuated. However, we now know from modern medicine this really does serious damage to your eyes retina. So, yes, indeed, Galileo actually used the method of projection. I believe he had a pan full of water, didn't have a mirror at the time. He could have used speculum or something else, or maybe a piece of paper, but anyway, he chose to use water on a pan, and then he was looking at it from an angle, he was making these more things happen. Good question. All right, so rotation of the sun, blemishes appearing, disappearing, and something that probably we are very fortunate is that this happened at the time that telescopes were possible to be produced by other people as well. It's not that you were going to Walmart and buying a telescope, but you could, if you had the knowledge to build one, you could do it and you could see for yourself that the sun had blemishes. So if the church or any other person was, let's say, not willing to accept this as a fact, well, the joke was on them. Everybody could see that for themselves. That was the amazing thing at that time in the 1600s. That's where science really changed. Up to that time, everybody believed Aristotle, that Aristotle considered the sun as a perfect sphere, right? So, okay. Said good things and bad things. All right. Now we fast forward a little bit more, going into the early 1800s, where the first theory of what those spots on the sun were. And William Herschel, those of you who are really into astronomy probably have heard that name before. He was a legendary or famous figure in science and astronomer himself. He was the royal astronomer, appointed by the king himself in England. And his theory about sunspots was that there were actually holes on the crust or the surface of the sun. And when they were appearing, you could actually get a glimpse of what is underneath the bright surface of the bright envelope of the sun. So holes. And he also theorized that people were living under that without having any evidence, but you see, temptation is we struggle with sometimes. All right, so he was the first one not only to have a theory about sunspots, but he was the first one to also observe the so-called granulation, which is really kind of the surface of the sun bubbling the same way a cooking pot, when you boil water, bubbles here and there. That's pretty much exactly the same thing. This is actually a zoom in into the sun by many, many orders, not of the same magnitude, but a very, very deep zoom using a telescope in the Canary Islands that actually operate about once a year. I go there for my own observations. I actually make a composite page zoom, so that I use a zoom lens and a telescope, but I combine multiple images together. All right. So granulation, we saw how it looks. Now the eclipse. Now everybody talks about the term solar corona when they're looking at the eclipse. That's the feature, not the moon going in front of the sun. That's what causes the effect. But what you see once the moon goes in front of the sun is this diffuse glow. This is known as the corona. Turns out the first time this was used as a term was back in 1809 by a Spanish astronomer called Joaquin de Ferrer. And that's what he recorded. It looks like an engraving of some sort that he made to take a note of this event. And he called it corona because in Spanish, corona means a crown, or in Latin, it means the crown. Like he's looking at the king's crown on the top, looking top down. And you probably imagine why he said that by looking at this figure. But in reality, what he might have seen, that's a modern image, actual photo of the solar eclipse. Narrow angle, of course. So yeah, you have to use your imagination. It's not going to be perfect. Radiant spikes all around the sun, like a Japanese flag or whatever, right? So it's not like that. But anyway, close enough. Now we go a little bit back in time, to the time of Newton, legendary Newton himself, back in 1666. That was the time that London fire completely destroyed London, for those of you who are in history. At the same time, there was a major pandemic of the kind that we suffered a few years ago, in the sense that people were dying and people had to really isolate for their own good. And that's what Newton himself did. He was actually a student in Trinity College in Cambridge University, and he had to stop his studies in the middle because that was the way things had to go. And out of his boredom, actually started playing with a prism. He made a hole in the window to allow sunlight to go through. He used a magnifying mirror and a prism, although he could have also used as a prism. And then the light coming from the window ended up being casted onto one of the walls that were in his room. That's his actual room in his family's house. And that's his own drawing. Now, a modern artist might have a different impression of how it will look. But in essence, it's the same. You have a hole in the window, covered otherwise completely, so you don't have light entering the chamber in this kind of way. Goes through this prism, and then light gets analyzed in multiple colors. So he discovered by doing this simple experiment that white, visible light coming from the sun is composed of all the possible visible colors, because that's everybody can do this experiment. That's the beauty of it. And then he actually could use another prism and try to see if he can really split more colors and see colors he haven't seen before. Well, it turns out he failed on that. If the visible color cannot be split further when another prism is used in series. So, quite an important discovery, but he missed something. And that something was picked up almost 150 years later by a gifted gentleman called Joseph von Fraunhofer. He was I believe from Austria, and he is considered a very important figure in history of science because he did exactly this figure, which is the drawing, hand drawing, he himself did, piece of paper of the solar spectrum. By using prism of better quality than Newton himself had available in 1666, he was able to actually see dark lines, missing colors in the color that is emitted by the sun. Here it's in German, it says red, orange, yellow, green, blue, indigo, and violet. Nowadays, of course, we use actual numbers. Mistake, 700, close to it. But at any rate, what he showed was exactly that. That the light from the sun not only has missing colors, but here this graph on top corresponds exactly to the brightness of how this looks when you use your own mirror, your own prism. And he actually found that the light is actually peaking out at around yellow to teal or greenish color. So he was able to measure that and document it. He was the first person in the history of science who did this kind of graph without using any computers, by the way, right? Just understanding what he was saying. And here you have all those designations here, picking particular missing colors in the spectrum, which turned out to be very important, of very important significance later on in understanding not only the sun, but other stars in the universe itself. Here is himself in a painting, posing in front of his spectroscope. Another thing he did it again, meaning he does it again, he does something amazing again. Not only he was the first one who understood that the sun's light is missing some colors in there, but he also created a new instrument, a new element, which behaves similar to a prism, which is called diffraction grating. Some of you might have heard of that. Those of you who haven't, it's all right. The idea is that you can use this thing, and this is basically something you have seen from your experience. When you look at the CD and you look at the bottom end of it, I guess, with some light, you actually see that, it appears very colorful. That's exactly the principle of the diffraction rate. That's exactly what the prism does. Why does that happen? Well, that's because the CD, or DVD nowadays, has a groove spacing, the same way an LP, a regular old style record, has grooves. Same thing happens in optical media like a CD or DVD, only that it's actually much finer. Well, for a CD, everybody uses DVD, so it's much finer anyway, contains more information. For a CD, it was 0.0015 millimeters. Well, look at what Fraunhofer managed to do using his own instruments of that time, only twice as bad as the CD group spacing. We're talking about 1821. And he did that. So once you have light falling on top of such an element that has grooves, imagine vertical grooves going this way, you will actually get the spectrum of any light falling there, which means the light will be analyzed automatically in that fashion, similar to a prism. Now, why this is important, why did you bother to put the slide together? Well, that's because nowadays we use such methods and we don't really use prisms. They're performing much better for what we need to do. And plus, you have the experience from at the bottom side of the CD, so you know exactly how this looks. You don't need to buy one to see how it works. Anyway, another important figure in understanding how things work outside of our own planet was this gentleman here, Christian Doppler, back in 1842. He was a PhD student, and he proposed in his thesis that, well, what we now know as the Doppler effect. It means that relative motions are actually causing light to change slightly. And that slight change will be completely impossible to determine with our own eyes, but because you need to go fast. When I say fast, you need to be going at least 10 kilometers per second or something like this. And per second, it means, we're talking about faster than a bullet. But those are actually common speeds in astrophysical objects. And he actually theorized that, he was looking at binary stars, and binary stars were known at his time that were rotating around their common center of mass, which means that if you are in the audience, you're looking at the binary star, and one star is moving closer to you, and the other one, as it rotates around, the other one moves away from you. Well, the one that is moving towards you will actually have a bluer, or it will have its spectrum shifted because of this relative motion, and the opposite shift will happen to the others. So this guy figured that out, more than 150 years ago without having any modern instrumentation. It was just theoretical work. And of course, some luck, because it was a hypothesis, but looks like he had the talent, he made the right hypothesis. So with this effect that now it's named to his in his honor, we can understand motions that are moving or towards us or moving away from us, whether they're galaxies, whether they're solar material, explosions on the sun and whatnot. All right, you might have noticed it when you drive by fast-moving ambulance, for example, the change of pitch. That's exactly the analog in they sound. All right, that's one important thing. The other important thing was the invention of photography, which happened about late 1838, 39. Around 1842, it was applied readily in astronomy as a tool. Because remember, how meticulous all those previous early observers were in taking records of what they were seeing in the telescope, with some, of course, possibility for subjectiveness, not objectiveness, because it depends on your skills, whether you really record something that you see in exactly the same manner. So photography solved that problem once and for all, but it took some effort, and it was these two gentlemen from France, Hippolyte Fizeau and Léon Foucault, who managed to take the first photograph of the sun, talking about the sun. And we can actually see for the first time sunspots, how they look like, recorded on the photograph, on the picture, and not by hand. All right. How many of you have heard the so-called solar cycle? Well, that was also discovered almost the same year as photography was applied for the first time in astronomy, but that wasn't a tool that allowed us to discover the solar cycles. Turns out, around the beginning of 1800s, so let's say the first 30 years or so of the 1800s, all the rage was to discover planets. And there were theories about planets far away from Uranus or Neptune. Well, Neptune wasn't discovered at that time. Pluto for sure not. It was discovered back in the 1930, almost 100 years ago. All right. But there were also theories that there was a planet that was actually revolving closer to the sun than even Mercury orbits the sun. There was a name that kind of stuck. Everybody was looking for planet Vulcan. Vulcan, They must have been very, very hot, like lava. So that's really what I call it volcano. All right. So he had to do what? He had to hope that every day that he observes the sun, he takes, meticulous measurements by making hand drawings of what the sun looked like, including the sunspots. And he was hoping that over all those years, and he actually did that between 1826 to 1843. He was hoping that he was going to see in post-processing, after he had all this large data set, by eye, flicking through pages, whether he's going to see a planet transiting in front of the sun. Well, turns out he didn't. But what he discovered was even bigger. He found that the number of sunspots increased and decreased in a regular pattern. Yet he managed to capture 2 solar cycles between 1820 and 1840. These 2 here. And then, once you have 2 of these happening with somewhat regular length, which is about 11 years, he made a prediction. Prediction in science is where you say something, you hope it's right, but you also expect that somebody else is going to verify it or disprove it. It turns out it didn't take long, a couple of years later, other people independently verified his results. And of course, that continues up to now. There is a graph here with all the blue spikes. Every spike is the peak of a solar cycle as measured by the number of sunspots apparent on the sun. Of course, you have to do some averaging, you have to come up with a metric that is consistent. The different observers here that are contributing to this data set. So there is some degree of subjectiveness, but anyway, the point is you can see fluctuations. And indeed, there was a time between 1650 all the way to early 1700s that the sun did not produce any sunspots. So people kind of lost also interest in taking recordings, but every now and then somebody was looking. And that's what we see with those X points here, actual measurements. And this we know nowadays correlates with a time that the sun was emitting less intense radiation. And that caused the so-called little ice age that happened around those times. I'm talking about rivers were freezing in Central and Northern Europe every year. I'm not talking about permafrost, I'm talking about, 10,000 years ago, whatever the conditions were. But it was an actual thing that is also depicted in paintings. So it's a fact, we know that. So the sun seems to have been the culprit behind this lower activities. And of course, that translates into a smaller number of sunspots at that time. Now, this is where astrophysics is born, with the invention of spectroscopy. Remember what I said earlier about Fraunhofer? He was the one who made this painting here, the drawing of the solar spectrum with the missing wavelengths, missing colors. Well, 2 fellows from Germany, Kirchhoff and Bunsen, they used Fraunhofer's instrument of their own construction, and they decided not to point it to the sun, but they decided to point it to, let's say, a burner, which is just a low intensity fire that is burning completely fueled by gas, and then sprinkle material of any sort and see what kind of light it makes. Some of you might have used gas stove in the past, and maybe when we throw some salt, you might have seen some flash coming out of it, and it usually appears very orange. Well, that's exactly what they did. So they found that this particular line missing from the sun corresponds to sodium that is actually in the salt crystals. Amazing. That's why I call it not just me, but historians of science, that's the beginning of astrophysics. Because now you can really link physics and experiment that happens on the ground to understand what happens on another astrophysical object, for example, the sun. Another thing that is important besides that, because we're talking about the sun, well, apologies for the pixelated image here, is that another guy who you'll see in the next slide that have his highlight, not that this is actually a video, discovers that the sun does not rotate like a solid body. So when you look at the flipbook movie that I played earlier about Galileo's drawings, sun drawings, that the sun is rotating, it wasn't very apparent what this is about. Well, what this figure shows it tries to illustrate how the sun really rotates. And now we know from measurements that this guy did, and of course it's a fact. And it was being replicated every single time. So if you have two sunspots, for example, appearing at different latitudes, this is the equator of the sun, and this is a bit higher, and you wait, you give it a few days, then you'll find that the one on the equator moves much faster. It's not a projection effect. It moves literally much faster than the one that is actually in the northern hemisphere. And then give it some time, the difference will be even bigger. So those of you who are interested in numbers, the equator of the sun rotates in about 25 days. And anything closer to the poles rotates 10 days slower. So it takes 10 more days than the equator for a full revolution to happen. That's an important point, so hold that thought. The sun rotates differentially. Now that's the big deal here. That's the.
I'm the only one who notices the uneven quality of the sound.
Actually, was one of the two people who observed on that particular day on September 1st, 1859 from England. The other one was also in England, the other guy called Hodgson, Hodgson, Hodgson. Also Richard, really, same first name.
The speaker keeps moving away from the.
So both of them observed the sun at the same time because they were curious to take their own hand drawings of the sun. No matter whether there was photography available or invented, people were still taking hand drawings as well. Here I did my own pasting of an actual photographic record of the same region of sunspots that was kind of observed on that particular day, September 1st, 1859. Well, as he was observing for about an hour or so, he suddenly noticed something that he hasn't seen before, and he was a seasoned observer, at least 15 years, he was looking at the sun with his telescope. He actually saw two bright arcs on the sun, on the vicinity of this sunspot region. And anything that you see here that is dark, it's Carrington's hand drawing, by the way, in a publication. This corresponds to sunspot area. Anything around it's not just brights. But here, those bright features that are indicated with A, B, C, and D, these are even brighter than the average sun. And that's what a flare is. And that's where the name flare came up. However, one thing to point about here is that was a serendipitous observation. There was no such event since then that was observed on the sun. Why? Because at that time, we didn't have the technology. Carrington and other people all over the world were only able to observe the sun in this kind of format, in this kind of way. You could only see where the sun is, like what is its extent, and sunspots. That's all you could see. Well, he noticed this very bright features. He thought that his telescope got damaged, so he could see directly light coming from the sun. So that was his first reaction. It's all documented in his paper. I'm not making it up. You can read his original paper and you can see for yourself. It's interesting how he describes it. However, 15 hours later, intense geomagnetic activity happened all over the planet. People, as you might have read, in the United States, especially people in higher latitudes that were working in the lumber business, had to wake up. They thought they had to wake up, or they were late in waking up, so they had to actually cut trees. And why they thought about it, it was 3 a.m. in the morning, for example, and they could see bright skies above them. Not because it was really bright, as in the sun is out, but the aurora borealis, the northern lights, were so strong that it made them believe, oh, we better make up breakfast. And they did. Other things happened, for example, telegraphy was pretty much implemented throughout the United States and other countries in Europe. And it turns out that they had problems. They could not really send signals. I mean, there are lots of stories that have disconnected batteries, and they could actually send signals without a battery, which was really bizarre. It could kind of defied physics for them at that time. Turns out it was just the sun's energy impinging on our planet.
Yeah, I'm not sure if this is related. But
Yeah.
One of these telegraph stations about fire.
Yes, yeah, I read about that as well. Yeah, it's possible. Yeah, short circuiting, and excess energy. Yes, or it could be somebody who was forgot to, I don't know. But that's indeed something I read about as well. So, anyway, so that's if anybody has mentioned before to you the Carrington event or the biggest solar flare ever. That's the event. We haven't seen anything like this since then. That's why I put a slide like this. How are we doing in terms of time?
45. We're done. You got a little bit of a late start.
All right. So 25 minutes or so, something. All right, cool. So here's so as you see, I'm taking you step by step to see the whole development. How we started to understand that the sun was not, it was not, just something people used to worship in the past, but it was an actual astrophysical object that we could learn a lot about. Well, it turns out, many people were involved. It wasn't a one-man job. There was this gentleman from, in fact, he was a Father Angelo Secchi. So he was a man of the church. He was the head observer of the Vatican Observatory in Italy, and he used his own telescope, and he actually proved for the first time of these red objects are these red flames that were mentioned, noticed over the millennia. Started mentioned back in the 9th century in the Chronicle I mentioned before, were actually solar features. In the past, people thought that these red features are lunar features that they get backlit by the sun, that the sun is behind the moon. Well, it turns out he proved that he could see such red features using a spectroscope, not directly seeing the shape, the structure, but really verifying there was excess red light coming out, even in broad daylight, without the eclipse happening. So he proved it was of solar origin. Amazing stuff. Guys, these people were really, really geniuses. All right. And this is another amazing eureka moment in astrophysics. Because this guy here, called Huggins, he was, from England. And he started as an amateur astronomer, but he ended up becoming the chair of the Royal Institution. So imagine that. Because of his discoveries that he made as an amateur astronomer and looking at the sun. He used this instrument here, which is, they call it train of prisms, because you have 1, 2, 3, 4, 5, 6, 7 prisms arranged this kind of circular way. Why they are arranged such a way? Well, because when light passes through a prism, it actually bends. So you cannot just make a train of prisms look like a Toblerone chocolate, right? You have to bend it around and actually leverage the fact that you want to use this prism so you can get the light dispersed, attenuated as well, but also dispersed so you can really select the particular wavelength you want. And that's exactly how they did it back then, without using the refraction rating, just using prisms. So yes, we had Fraunhofer in 1821. This is 1868. Sounds like going back to old fashioned, but well, it turns out that could not work with refraction ratings. It could work with prisms. And the point here is that he also took the liberty. So here is the sun casted on a metallic plate. So you can see here some sunspots. And here, basically, this represents the edge of the sun. And now I said earlier that Angelo Secchi pointed a spectroscope with a slit, having light coming through the slit without being able to see lumens. But turns out, using this instrument, when he opened the slit into a slot, slit is like, we use the term slit in physics and experimental science to describe that we have a very narrow opening. And when you use the term slot, it actually supposed to mean that you have actually widened it a lot. It's a little bit wider. So he took the liberty to widen it, something nobody else did before. And after doing so, lo and behold, he would have said, if he was showing that to you, he could see prominences on the sun without waiting for an eclipse. And that's his own, actually, I'm not sure if his own engraving, maybe it is. It's from a paper from an American professor that was probably back in the 1870s, reflecting on this discovery, a couple of years later after it happened. So you have that, and by using this new technology, you could then observe the sun without needing photography, just with your eyes, without worrying that you're going to burn your retina, because all those prisms really attenuated the light for you. And you could see all those structures that really, if you look at them, those are actually hand drawings, paintings by Angelo Secchi, the other guy who made this contribution before this discovery, how to observe the sun. His paintings. Using this technology, this approach. And that already told us a lot about the sun. Going back to the other guy, Huygens, who I mentioned earlier, was the one who discovered this technique. This guy really had a talent about discovery. He also took a picture. This is a picture replicated as an engraving of solar prominence. So he not only he was able to see them live in a live view through the spectroscope, through a telescope, of course, looking at the sun, but he also piggybacked, an early camera of that time, and he took an image. So that's one of those prominences that we saw. Now, this technology, though, cannot be used to observe the sun on the surface. Might have to skip that, although that's interesting. Well, all that really showed that the chromosphere, those red flames, were not just a telltale sign, it was the proof that the sun didn't just have a surface, which is the photosphere, and the corona, which is the extended dilute atmosphere that you can only see during the eclipse, but it had an intermediate atmosphere called chromosphere. And this guy here coined the term chromosphere. He knew some Greek, I guess, and he made a compound word, which means sphere of color. So at that time, people thought that, you had this material that was giving color to the sun, or was removing color from the sun. That wasn't the idea. So the biggest discovery, or the biggest breakthrough after all this amazing series of developments, every decade it has something new. Well, that was also the continuation of that, was the discovery or the invention of the spectroheliograph. This instrument that was developed simultaneously by those two people, one working in the United States, he was an MIT undergraduate, and this guy was an astronomer in the Paris Observatory at around 1892, independently, without communicating with each other. They just developed the same instrument. And images from that instrument look like this. It was the first time you could see the surface of the sun in different wavelengths. Before that, you could only see anything around it. So that really was, complete opening of the door for astrophysics, in particular the study of the sun, which is the object of classical astrophysics. So basically, how you make that, you have a spectroscope, nothing new there, but you have to use a photographic plate. And the way you do that is you have a slit, you scan the sun the same way a scanner, you remember the scanner, you're putting a piece of paper or a Xerox photocopy machine, works exactly the same way, only that doesn't print out the paper, it just exposes a photographic plate bit by bit at the particular wavelength you choose. And that was all done with mechanical means. And you can see a schematic, those of you who are savvy of optical designs, you can probably see for yourself how this worked. And here is how things look. That's a modern implementation of the same instrument, but you can see here different wavelengths. The different wavelengths, you see the entire sun here is a zoom-in view, and you can see what is now called here a filament, which is basically if you rotate the sun this way, you put this B at the limb, that becomes your prominence. And that was basically proven or discovered in the 1890s using the spectroheliograph. Before that, you didn't know what it was. You just talking about these as prominences. So now you can see that, and a new term came into use called filament because it had the filamentary structure. Really resembled the filament of a light bulb or something, more or less. Say it again?
Where are they?
Where are they?
What
they are. Those are basically, these are features suspended above the solar surface. Think of them as clouds, but they're magnetic in origin. They have magnetic fields penetrating them, and magnetic fields act like a bottle that can hold material. That material is actually dense and cool than the rest of the sun. That's why they look darker. So they're just suspended. So if the sun, as I said earlier, is about, like the size of a basketball, and the Earth is about what? We mentioned a 16th of an inch, which is about this sunspot here, roughly speaking. This is sort of suspended about half of that from the surface of the sun. Half of a 32nd of an inch above the sun. That's where you find. Now, this is in a quiescent condition. Usually these guys like to erupt. And when they erupt, they actually rise and rise and rise and rise to the point they completely escape the gravitational pulled from the sun. They become material in interplanetary space. That's really the actual explosions, the so-called magnetic explosions on the sun. I think I should skip all that. This is, if you guys had technical questions, maybe we can revisit that. That's really the most important thing in astrophysics. Maybe I'm biased, but many people will agree, is the discovery that magnetic fields play a significant role in the universe, including the activity on the sun. So anyway, there was a Nobel Prize given for this discovery as a laboratory experiment. When you have strong magnetic fields, the spectral lines that we discussed earlier, the lines that will be missing from the sun, they actually split into components. And that's exactly what was proven by pointing a spectroscope at the core of a sunspot to actually see that a single spectral line splits into three as you cross the sunspot area. So all this length here corresponds to the spectrum that you see on the right. And turns out this split, the separation, is exactly proportional to the strength of the magnetic field. So you were able to measure, and you still are, the strength of the magnetic field on the sun without going there with a magnetometer or with a magnet. Yeah, just the remote sensing. Yeah, pretty amazing stuff. Anyway, I should probably skip most of these. Maybe I should show you some movies. That's also interesting. Yeah, about 100 years ago, the same guy, one who developed the spectroscopograph, Hale, Georgios, an American astronomer from California, I believe. He not only made the first measurement of magnetic fields on the sun by putting his spectroscope slit on the sunspot, but he also did that in a systematic way. So he made survey over, I don't know, 2 solar cycles. So back in the mid-20s, 1920s, he actually determined that when you have sunspots, first of all, they seem to be appearing in pairs. And turns out one pair has one polarity of the magnetic field, the other one has another polarity, which suggests that magnetic fields are emanating, perforating the center of the sun. They're coming from inside the sun. They make some sort of trip above the surface of the sun on the atmosphere. Then they plunge back into the sun. That's really what north and south means in this context. So he found that in the North Hemisphere, all these regions, the bipolar sunspots, had the same orientation and how the north-south, where the magnetic field is coming out and the magnetic field is closing back into the sun. And that was reversing if you were observing such regions in the south hemisphere. And not only that, he actually figured that at the end of the solar cycle, at the beginning of a new one, this trend reverses completely. And that happens in a regular basis. And now we're talking about 11 years solar cycles, but that's about the sunspot number. In reality, if you want to count the fact that the magnetic field actually changes polarity with every solar cycle, you have to be talking about a 22-year long cycle, because that's the cycle of magnetic activity. All right. That's also interesting. In the 1930s, up to 1930s, as you realize, we only understood the sun as an astrophysical object, and only through its atmosphere. We couldn't really delve into the sun and understand what's powering the whole thing. Well, turns out it was nuclear fusion, and only because of quantum mechanics it was possible to explain that. It was Hans Bethe, this guy, the professor at Cornell, back in the 1930s, who actually came up with the right answer. He got the Nobel Prize in 1967. So anyway, different stars have different stellar structures as a result, because we understand how fusion happens. All right, 1940s. That's the invention of the theory of magnetohydrodynamics, or MHD in short. That theory is a powerful theory that probably describes 99% of the universe. Why? Because 99% of the universe is actually made out of plasma. Anything else is non-plasma. And plasma follows the laws of magnetohydrodynamics. Plasma likes to follow the magnetic field lines, or even shape them, or change orientation, for example. And this is how that theory allowed us to understand why sunspots are dark. Sunspots are dark because magnetic fields, I'm not going to show you any math, but magnetic fields are perforating the surface in this kind of manner. Anywhere else, you have the so-called granulation and convection currents that are bringing hotter material from the core of the sun all the way up. But then here, when you have strong magnetic fields, the magnetic fields act like insulation boxes. The same time you use, when you, I don't know, you have, you want to keep your beer cold or your ice cream not to melt. So that's exactly how this works. It kind of isolates the transport of heat inside those magnetic field connections. And that's why sunspots look dark. Otherwise, they will have looked exactly the same way as the rest of the sun. Anyway, yeah, just an ink. I'm going to skip that. How did we understand everything about how the sun generates a magnetic field? Well, that was only possible when we're able to make maps, not just placing a slit on over a sunspot and measure how the spectral lines are splitting to measure the magnetic field, but do that in a systematic way. And this fellow over there, Horace Babcock, was the one who came up with an electromechanical system. I mean, these guys were really, I'm talking about them, I have given talks about that many times, and every time I'm talking about such things, it just fascinates me how they came up with a way to make this work. So you see, originally they were using an oscilloscope screen to show the polarity of the magnetic fields, but it was really difficult to read it. Then he came up with another slanted lines orientation to tell whether it's positive or negative polarity, and the grayscale was just the intensity. But nowadays, those are two instruments that our lab at Lockheed Martin has built back in the early 90s and early 2000s. And they're still in operation, both of them. These are actually operating in space. These were operating from the ground. So in space, they look more like actual pictures or images. Okay, I'm going to skip that. That's the solar dynamo process where magnetic fields are generated. This is back in the 1970s. Some of you might remember Skylab was the first United States space station. And this is where we closed our understanding in terms of how the solar corona is energized. And it was possible for the first time to take images continually from space in X-rays. There's no way you can do that from the ground because the atmosphere isolates, X-rays. So you have to go to space, and that was the first time this was done. Here's a movie that shows the so-called coronal holes. So it turns out there are every now and then holes in the solar corona. When I say holes, think of it as holes like, okay, you have a hole on a window of glass. The hole doesn't mean that you have a vacuum there. No, there is air. So similarly, it's not that it's completely in vacuum, but it means that the magnetic field lines are actually completely open and allow for material to escape in the form of solar wind. So these were only seen from space in X-rays. And now we do that routinely with instruments we have built at Lockheed. And that's the instrument I want to highlight before we finish for today. So this instrument operates since 2010. It's called the Atmospheric Imaging Assembly. So I didn't write it explicitly, AIA, that's why, it's there. Maybe you can hardly see it. And it observes the sun at different wavelengths, from ultraviolet wavelengths, expressed in angstroms, all the way to close to X-rays, where typical X-rays start at 1 angstrom, and those are not really hard limits. And the colors that you see here it's the same image of the sun taken at exactly the same time, only that it's taken at different wavelengths. Now the colors are false colors. We just put the colors there to prettify things. It doesn't add more value other than understanding, when I see green, I mean this wavelength. That helps us scientists to communicate better. But other than that, you can see lots of similarities. So when you have areas that are very bright, they look very bright overall, right? But you also have differences, not just in terms of colors, but in terms of brightness. And this is how the telescope looks like. Actually, it's a series of 4 telescopes. That's why we call it assembly. It's an assembly of 4 telescopes, each of them capable to observe in at least 2 wavelengths. So that's how you cover the entire spectrum. I have a dedicated satellite that is basically in an inclined geostationary orbit, which makes an annealing of an figure 8 shape, moving above and below there's equator in projection. But that's necessary so that you can always have a downlink in our ground station in White Sands, New Mexico. And that way we can monitor the sun 24/7 since 2010. That's exactly what we've been doing. And I hope the next one is actually a movie. The United States Postal Service honored us by making this collection of stamps. I think that was back in 2022. I'm not sure they're around anymore, but anyway, that was really nice. So images from a particular a particular choice of images from our telescope of the sun. I'm going to skip that, although I think this is interesting. Just quickly, what you just saw is an actual observation of the sun at a particular region where you have a filament. And that filament, as I mentioned before, is basically cool material that is suspended on magnetic field lines. And these magnetic field lines are basically, as we know now, they are twisted, like a braided structure, like a slinky. And because they're twisted, that's how they have dips, upward dips, as the magnetic field lines are doing this kind of thing around an axis. And that's how they can hold material which is basically ionized, right? That's why they have to be bound on the magnetic field lines. And turns out, as the structure, I'm going to play that movie really quick again. Boom, that's a flare. That's a solar flare on the sun. Most of them do not behave like this. Most of them actually like reject material outwards. I'm going to show you in just a few seconds how, and that's a simulation of the same event. But that shows we actually have a good grasp of the physics, because we can confirm our hypothesis. The mathematics is correct with what we see in the observations. In comparison. And here's how a structure like this will look from the top. And we literally see them quite often before explosions on the sun. So that's kind of a way that we can probably issue early warnings eventually. We don't have this capability right now. No, we don't. But eventually we might be able to maybe even use machine learning, for example, or something more clever than machine learning, who knows, to be able to make such predictions before such features explode, such filaments.
What's the meaning of MFR there?
Excellent question. Well, it's an abbreviation that stands for magnetic flux rope. It's a rope-like structure, as you can see here, and that's what this suggests. In this kind of simplistic toy model or cartoon drawing, looks like a rope. A rope is actually a twisted structure, and magnetic flux is basically the same thing as saying magnetic field. So it's a magnetic field rope. But that's a cartoon model understanding. And here you saw the movie of it. Now, when such explosions happen on the sun, they release an intense amount of X-rays that comes from the bottom end of the structure.
So the spots come in pairs, there's polarity, and there's a field between and many of the phenomena.
That's an excellent question.
Around that.
I see where we're going with that. One idea is that you have two sunspots. One is rotating, maybe the other one is rotating too, but not in a way that when you rotate, you twist the magnetic field and the other one is untwisting it. That's one theory. We don't see that very often. What we see instead is that you have not just one bipolar sunspot or a pair of sunspots, but we have multiple pairs of sunspots clustered in the same small area on the sun. And once this happens, these sunspots have their own proper motions. They just like to move a little bit. But as they move, they might collide with opposite polarities of other pairs. And that's what we tend to actually think nowadays is the reason behind this twisting. I have specific slides to explain how this works, but I don't think I should do that right now. But if you're interested, stick around. I will actually show that to you. So once this untwisting of the magnetic fields happens, because they are twisted in the beginning and then have to release that tension, that energy, they emit tremendous amounts of radiation. This is expressed in ergs. Those of you who are really into that business, you understand what that means. Otherwise, think of it as that. 1 million times the yearly United States electricity production. Just one event on the sun, and a small one, not a big one. It's about 10 million times greater than the energy released from a volcanic explosion. Remember when was the last time a volcanic explosion on the news? Think about that the sun can actually do it 10 million times in just one event. Well, it's 100 times bigger than the Earth, right? And 100 million times greater than one H-bomb, fusion bomb. Not the one that was thrown in Hiroshima and Nagasaki, but the big guys, the megaton ones. 100 million times then. Yes.
In what form is the energy emitted?
Excellent question. Kinetic energy, propelling material upwards, giving energy so that they can escape the gravitational attraction. The other one is in terms of light. Light will actually propagate freely outwards, and that's where most of this energy comes out as X-rays, highly energetic radiation, high frequency radiation. Excellent question. Well, I'll show you that because this shows 40 Starlink satellites plunging into the Earth after a period of intense activity on the sun. Yeah, they actually became, vapor, whatever. And that happens quite often, not just with Starlink satellites, but it will happen more often because Elon Musk wants to deploy more and more of them. So yeah, now he's at around what, 3,000 or 4,000 of them. He wants to go over to 12,000. So what happens is when a flare on the sun happens, a big one, it hits up the Earth's atmosphere from the side that is actually radiated by the sun. And as this happens, the atmosphere puffs up because it absorbs that energy. And as it absorbs that energy, then the satellites that are orbiting in this low Earth orbit, because that's all the money he has to spend on this, Elon Musk, he would have gone a bit higher. So he has to save some money by putting the satellites in low Earth orbit. However, the drawback there is that the atmosphere will puff up, and then the satellites will start to experience more friction than they used or they are designed to experience. That means they will lose energy and will actually fall, plunge into the Earth through the Earth's atmosphere. They're not going to end up in your backyard. Don't worry about this. I think that's too small. But he's gonna be losing money every time this happens. So he has, as much as we want to actually, those are still the same sun. So as much as we want to understand how the sun creates such events, there are stakeholders like the industry, space industry in particular, that are interested in protecting their own space assets, and not to mention assets that are of national security, right? So you also want to understand all that.
Is there a minimum or maximum diameter of the beyond which, if you go beyond the maximum, you would avoid most of it?
Yeah, totally. You can go to medium distance, for example, or other highly more distant orbits. You can put them in a geostationary orbit. The problem you have then is the coverage. So Elon Musk wants to have coverage around the Earth, so he can actually get all people's data and the convenience he offers that you can have direct connectivity to the internet no matter where you are, and do whatever he wants with your data, your personal life, sadly. But you can only do it with low Earth orbit satellites. Then it becomes an astronomical number that even if he gets a 1 trillion in his pocket, he cannot pull it off. So that's why he has to keep the satellites at lower orbit to make it happen. Yes.
Well, all this is happening on the surface of the Earth with magnetic flare and all that. What's happening inside the sun?
While the flares happen?
Just in general.
In general, okay. Nuclear reactions happen every single second. Every single heartbeat, that you feel. There are nuclear reactions constantly happening at a particular rate. If that rate changes, the sun will behave in a very different way. Turns out the sun doesn't behave in a different way, that means it provides the same radiation output constantly. There is some variation that we now understand has to do with the magnetic field modulation, which has to do with this 11-year cycle that I mentioned before. So when you have too many sunspots on the surface of the sun, one would quickly say, oh, because you have too many sunspots, you actually have the sun's surface covered with dark areas, therefore it emits less radiation. That's not what happens. When you have many sunspots, you actually have more radiation coming from the sun. That's counterintuitive. And the reason to understand that is, the only way to understand that is by looking at the data and looking at how the magnetic fields are actually allowing for light to escape more easily from the interior of the sun. That means the sun is radiating more energy. In periods that you don't have sunspots, you don't have that. You just have the minimum output of radiation of the sun. But that minimum is always sustained by nuclear reactions. It's not that the sun is switching off or anything. So that's what happens inside. The other thing that happens inside is, as I mentioned before, you have the differential rotation that really drags and distorts the magnetic field and winds it around like a what do you call it? Like a solenoid. Think of it as two donut-shaped structures, one in the north hemisphere, one in the south. That happens continually until the point that there is that much you can get out of it, or the sun cannot really accumulate more magnetic field like this, and then it has to really pump it through the surface. And that's where you have sunspots popping out here and there. That's how the sun gets rid of this twisting that happens in its internal structure of the magnetic fields and loses it with those explosions as well. Every of these explosions, what does it do? It unwinds the twisted magnetic field that the sun has been twisting and twisting and twisting under the surface. And it's released in terms of kinetic energy if material is expelled, or light, which is the most common way. You have X-rays radiating away this twist. That's really counterintuitive because it's about conservation of energy. But if you collect all those different numbers together, you'll see everything is really the math check. We are not missing any physics there. But what we are missing is our ability, in my opinion, to make accurate predictions, because that's how we will show that we have very good understanding of how the sun does all this magic. And not just the sun, other stars do the same thing again. That's a quick picture of all the satellites around the Earth. I don't know what else I should. Oh, I promised some movies. Let me show you one eruption here. It's a filament structure. Now, this is a tricolor image from our. Sorry, I was in the front. It's going to play again, I think. Here you can see a clock. So you can probably see for yourself how quickly this event happens.
This is with real data.
This is real data that happened back in 2012, August 31st. And actually, you can access that data yourself if you want. I'll show you the last figure. But that's not real time. You can see here for yourself the clock. Let me play that again. You can see how quickly. It's a time lapse. But it happens within what? Boom, within 20 minutes. It's out of the field of view.
These flares are directional, right? It's got to be pointed at us for us to get hit.
You mean the explosions? The flares radiate energy anywhere they
go
can
in-
radiate, which means in all different directions. But the explosion, I'll show you. I have a slide for that. You'll see. It propagates through the solar system. And if the Earth is on the way, it will be hit.
But it is direction.
It is direction, correct. But the material, not the flare, the material, the explosion itself, the expelled material is directional. I'll show you. Yes.
So what kind of thing is generating this imaging? Is it like?
Our telescopes.
Or is it using magnetic?
No magnetic. So
This is just plain out a full photons.
this is photons in the EUV or / X-rays.
Okay.
And this particular image is a composite of, let me play that again. It's a composite of 3 different wavelengths together, because that give us different views of different temperatures in the atmosphere of the sun. However, the material that was expelled was cool material, so it was dark in all wavelengths. That's why it was still dark in this sandwich of images. I have another one. Oh, this is a flare it produced. It was an M flare. When we heard of designations, some of you might have done your own research on this. The C flares, we have M flares and X flares. X flares are the most catastrophic. X flares are 100 times more powerful than a C flare. An M flare is 10 times more powerful than a C flare. So this is kind of an intermediate strength of an event. And you can see this is just a measurement for a geostationary satellite that shows the release of energy. So before that, nothing, boom. And then it takes some time to restore. And that's really the release of the energy that happened in tandem to all these motions you saw in those images.
How can you remember the sequence of what the flare means, like C, M? Is there a meaning behind or?
Good question. I didn't spend time to do that properly as a professor, but originally, when such a satellite, that's a different satellite right now, by the way, it's actually called Geostationary Operational Environmental Satellite, GOES, I think. And it's the satellite that the Weather Service is using to monitor hurricanes, in the United States. And there are 2 satellites. One is in the east, one is in the west of the United States. Anyway, too much detail. The point is, since 1975, the Weather Service, NOAA in particular, which is the NASA for the atmosphere of the Earth, decided to monitor the sun because they actually wanted to characterize this pathing of the atmosphere I mentioned earlier, how often it happens, and the best way to characterize it by measuring the total output of X-rays. In this case, is between 1 to 8 angstroms. So this is not any of the images I showed you earlier. Those were actually taken in the tens and hundreds of angstroms of wavelength. This is 1 to 8. So this is proper X-rays. Okay? And this shows you as a time plot. This is time here. And you can, hopefully, it's pixelated. Again, I apologize, but you can read it. Here's 3 hours, 6 hours, 9, 12. So every small tick mark is actually 1 hour. So you can see for yourself what range of times is actually covered. You can see for yourself how much the flare eventually lasts by looking at the time plot here. And here, because the question was about how one can remember what ABC is. So when they released this instrument in 1975, that we keep building it every 2 or 3 years to replace it in the same specifications. No, I didn't know, how to classify. The agency didn't really have a good plan about how to classify flares. So they came up with a plan to say anything that falls within this kind of energy, which is 10 to the power of 8 watts per square meter, is classified as A. Anything that is 10 times more is classified as B. Anything that is 10 times more is classified as C. And that's how far they went. Only to find out that when some bigger events happened, they had to introduce another one, and they call it M. And then they had even bigger ones, they call it X. And now we have the full enchilada of this, A, B, C, and X. That's all you have. A few more movies before, that's another explosion. That's, again, associated with a flare. The flare energy comes from below, as I mentioned before, but the acceleration and the expulsion of the material happens above that region where the X-rays come.
How far is this spell?
Oh, when this is successful, it goes all the way out in the interplanetary space and reaches the so-called, what is it? Basically it merges with the interstellar medium. When the Voyager satellite will cross the local bubble where the sun, the so-called heliosphere, every star creates its own sphere of influence. It's called, and not in terms of gravity, but in terms of magnetic fields. And we call those astrospheres. The sun, we call it heliosphere because sun, helio, you get the point, right? Helios means the sun in, I think, ancient Greek language. So all those explosions that happen, they actually propagate freely in interplanetary space. They lose energy as they travel out because they're not really moving in vacuum. They pile up with other material, the solar wind in particular. But eventually, they will actually reach the point that they cannot travel anymore because they're going to pile up in the wall that's created by that sphere between the sun's solar wind and the interstellar medium that has its own density. So the sun is constantly blowtorching its way through the interstellar medium that has a completely different density, completely different conditions, physical conditions, and magnetic field. So they are basically just, I don't know how to describe it. They're just being stuck and then diffuse or merge with the boundary of the astrosphere with the interstellar
So is
medium.
that the heliopause?
Yeah. There are many different. There is a heliosheath, there is a heliopause, then there is the heliosphere that contains both. So it does give you the broader perspective. But you're actually right. Yeah, there are different designations for that section of the sun. So and then I have a few other pretty movies with different colors. Again, that's a flare. There's a flare happening. That was similar to the other event that you saw. This is a filament escaping. So if you ever have gone to observe the sun on Saturday mornings at the Foothill Observatory that is operated by our Peninsula Astronomical Society, then you will notice around this time in the solar cycle that the sun is actually covered by such filament structures. We have a small telescope there mounted on the big telescope that is specifically designed to observe the sun. And you can see for yourself. Now, you don't want to see in real time such explosions, but if you are lucky, you might see the bright emission that is actually a flare happening at the moment. And you might see over time, if you stick around maybe for 20 minutes, you might see that the structure that was there is actually moving slightly, or it moved from how it was 10 minutes ago. And that's how it will appear to an observer. Yes.
So material that's coming out that you're imaging, that's being imaged, are they hot enough to be UV emitting, or they're not so hot that you're getting X-ray?
They are absolutely hot. I didn't spend time to explain that the sun's corona, and all you see here is primarily coronal material that emits in the ultraviolet. All these different movies that you saw. This is about 700,000 Kelvin right now. This is about 50,000 Kelvin. That's the lower end. Kind of this proves my point right now. Let me see what is the next one. Yeah, I'm just telling you based on the colors. This is 700,000 Kelvin, close to a million. What is the next one? I'll tell you what is the next based on the color. Because the colors are somewhat standardized. You know, I'm part of the team.
Wavelength, but all right.
Yeah, the point is, this is, the wavelengths are correlating exactly with the temperature. And that's why I'm trying to tell you that this is something that we know as working astronomers in that to interpret what we see based on the wavelengths. Because the wavelengths mean temperature. Temperature means something is happening there at that point. That's why radiating energy. Now, sometimes you see motions like the ones that you saw here. Other times you just see not a lot of motion, but you see a release of energy. All that is up to interpretation and understanding and modeling to figure out whether your hypothesis is correct or not. Now, that's a magnificent explosion, right? So you have material escaping the gravitational influence of the sun, but you also have material falling back down. When material is falling back down, it's called coronal rain. In the same way that this, the earth rain, the rain that we actually experience this time of the year in the Bay. But only that this is not made out of water. It's just a hot material, the kind that is emitting this kind of radiation that is gravitationally falling back down onto the sun.
What if we know in the cycle of the 11 years, magnetic fields going up and down?
That's a very good question. We have passed the actual maximum, the peak of the solar cycle. So we are about maybe a year after the peak. However, it's not uncommon after 1 year or so to see a secondary peak happening. We've seen it in the previous solar cycle, we've seen it in the one before, and many other times you can actually see double peaks in solar cycles. So maybe there is one that is imminent. The other thing is that the solar cycle, the solar activity doesn't really, it's not like a isosceles triangle. It's not really, it has one slope and the same slope going downwards. It actually has a ramping up phase, and then it actually slows down very slowly. Same way as the flares were behaving, that you had a very rapid, well, it's not as rapid as a flare, but you see the point. It takes time to restore. So we will have solar activity, significant solar activity over the following 2 or 3 years until we reach the point that definitely things have petered out.
Do you think that will influence the solar eclipse that is happening this year in August?
Only in a positive way, especially if there is a flare that something is spewed out, you might be able to see it, as a snapshot during the time that the eclipse allows you to see the atmosphere of the sun. And in fact, this happened a couple of years, maybe 4 years ago. It was an eclipse. I was really planning to put that figure in my presentation, but I forgot. Sorry about that. But if you Google it, you will see, solar eclipse, and you can write explosion or CME, coronal mass ejection. That's a technical term for the explosions on the sun. And you will see an actual picture of the solar eclipse that you will have been able to see with your eyes had you been observing that particular eclipse. I wasn't, too bad. But you could see an actual spherical-like structure. So if you were prone to believe this is a UFO, yeah, maybe that would have been you. But we know, because we actually monitor the sun 24/7, this was an ongoing explosion. That happened during the time that the moon went in the way, so you could actually get to see that in visible light, not in UV light. So one of the things I wanted to show you before we end is the efforts we put to actually understand the sun theoretically. And how we do it, we actually have a very, very ugly set of equations we need to solve. So we cannot solve them anymore by hand. Most of this analytical work has been done by smart people in the 40s and the 50s and the 60s. Now we have to use powerful computers like the one we have here at NASA, the Ames Research Center, supercomputers effectively, that we can use them to solve those difficult equations. And by solving them, the beauty is that we are able to, we have the computational power to generate scenarios that look very similar from initial conditions, as we say. We're not really guiding the whole thing to go in a certain way. We have initial conditions, and the idea is that if you get your initial conditions right, then the set of equations is all you need so that you can see the evolution of the effect materializing in the way we see in the sun. And that's one of such efforts that we did with our team a while ago, 2019. This is published in Nature Astronomy. And you can see here in false color the results of a magnetohydrodynamics, MHD, as I said earlier, short equation that shows with different colors, because when you have a simulation, you have a full universe in your hands that you can really colorize things in the way you want to bring out the details. We wish we could do that with observation, but that's not possible. So here you actually see with red color, for example, cooler material. With purple, you see hotter material, and with green, you see even more hot material. And that's why the green subsides later. And that's when the energy release in the flare happens. I think I have another one. Yeah, well, I can skip that. I can skip that. For those of you who are interested about how magnetic fields look like, I think you asked me how the collision can actually produce such magnetic field, twisted magnetic field lines. I'm just showing you not only that this produced with this simulation twisted magnetic field lines, but it also produced an explosion. And I'm going to play that again. You know, it's a time lapse of a simulation. It's not actual observations. You can see here, these magnetic field lines polarized in strange ways. They actually blow up and then they expand and they explode. So that's kind of a hypothesis testing we did. Here is another visualization, not done by me. I think that's from the Smithsonian, I think. So you see the sun, and here it gives you a kind of a perspective view of the solar system, at least the inner solar system. Here, I think this is Mercury, this is Venus. This is just an explosion that happened on the sun. We discussed earlier that it's directional. It goes in a certain way, in a particular direction. But of course, at the same time, it expands. So it covers lots of different directions. It expands. You see, it becomes a wall pretty soon. It's not just a sphere like a bullet. It expands in pancakes. And here is our planet, the Earth, being impacted by that. And as it is getting impacted by that, the magnetic field of the Earth is getting squeezed and squished. And by doing so, because those of you who are into the, I don't know, electronic engineers of some sort, you probably know Maxwell's equation. So you know that if the magnetic field is changed, it produces current. And that current has to go somewhere. It turns out the power grid is what is really able to sustain a current because it's all of that is conducting material. And that's why the power grid is actually overwhelmed by this squeezing of, that's another play of that simulation. So you see, this is the sun, and this is really much bigger than the sun. You know, with pretty quickly, let's say within 10 hours, this has become many times the size of the sun as a structure. Now, don't think of it as mass coming out of nowhere. This is mass that is spread out in the planetary space.
So how many of the planets have magnetic field?
That's a very good question. In fact, most of the planets have a magnetic field. Depends what your threshold of what you consider important is. Even Mercury has magnetic field. It has magnetic field that is fossilized under its surface. It doesn't have a molten core anymore. It doesn't generate magnetic field, but it has a fossil magnetic field the same way a bar magnet has. But that's very weak. And Mercury doesn't have an atmosphere. Venus doesn't seem to have magnetic field, or at least not in the sense that you would consider it substantial.
Yes, or does not?
It does not. But I'm not saying it's zero. I want you to be clear about this. The Earth does have magnetic field, and that's probably why we exist. The fact that we have magnetic field acts as an umbrella and protect us from all these vicious explosions from the sun. Because look at what they do to our planet. This is just a visualization, but it really gives you a hint of what happens. It really squeezes the heck out of our planet. And if there was no magnetic field, all this influx of material from the sun would have really blown away the atmosphere of the Earth, not at once, but bit by bit over the hundreds of millions of years. The same way when you blow a dandelion flower and everything really spreads out in the wind. And that's what happened on Mars. I was getting to that. Mars, has a very tenuous atmosphere. In fact, it's at least 100 times more tenuous than our own planet's atmosphere.
Does it have a magnetic field?
Because it does not generate magnetic field. It's okay. Once you're very clear. There is magnetic field, but it's not strong. That's why the question is, how strong? What is your threshold? You're not asking me that question, but I'm telling you, you have to keep it in mind. Otherwise, it will be confusing. There is some magnetic field, but it's not enough. It's not strong enough to really protect the atmosphere of Mars anymore, the way our planet is protecting its atmosphere through the magnetic field. And then if you go to the bigger planets, oh gosh, Jupiter, immense magnetic field, crazy magnetic field. It's obliterating anything that we have beyond the sun in terms of how powerful the magnetic field of Jupiter is. Same thing with with Saturn. Saturn has strong magnetic fields. Uranus, Neptune. The only thing we don't know, I think, is Pluto. I don't think there was a magnetometer on the New Horizons mission that really flew by Pluto. Plus, it was a very close flyby. I don't think they had the ability to do this measurement. So anyway, short answer is most planets have magnetic field. The question is how strong it is, and that how strong it is depends on what you really want to address. If you want to address habitability, we already know Mars doesn't have enough magnetic field to maintain a thick atmosphere anymore. It just gets blowtorched by the explosions. And to close, this is one of the positive outcomes of a solar explosion. Colors of the aurora. Those of you who were here a couple of years ago in the Bay Area, I mean, when there was this monstrous explosion in 2024, May 10, might have seen this. Maybe not with your eyes, maybe with your phone. And maybe let's raise some hands. Anybody has seen the Northern Lights in the Bay Area? No? A few. We have a few. Okay. All right. No worries. There might be another one. So, but I cannot promise. Coming up, I mean. So that's how the color of the aurora looked like, because we are at a very low latitude, and the material that is streaming from the sun that somehow gets channeled through the magnetic field of the Earth, somehow, I'm not going to cover the how, but the material from the sun is actually cascading all the way down to our atmosphere, from the sun, through the magnetic fields. And as this happens, it collides with atmospheric molecules of the Earth, and that can give birth to different colors. Now, aurora happens at all times. Those of you who have gone to northern latitudes, for example, I was in Juneau, Alaska in the same year, I got to see two different auroras with different colors. Turns out this is all you see in Juneau, Alaska, most of the time, without any explosions, because you constantly have the solar wind from the sun, irrespective of how strong the gusts are. And that will give you a green color because the magnetic field at the northern latitudes of our planet allows the material from the sun to actually cascade and penetrate deeper in the atmosphere. And because it's deeper, it allows for the green color to be seen. But if you are at lower latitudes, when there is a huge explosion like the one that happened in 2024, there is only that much the particles that can actually go as deep in the atmosphere of the Earth. It doesn't go as deep as you are constantly as you experience constantly when you are in northern latitudes. And that way, the conditions are different, and the same molecules, both of them are actually happening close with oxygen. But at higher altitudes, that the material is actually colliding from the sun with the upper end of the atmosphere. Again, the collision is not the kind that really kicks out the molecules from the Earth. This happens within the umbrella of the Earth. It's just that there is an opening, a crack in the door, and material is actually funneled through the magnetic field of the Earth, and that's how aurora happens. So this happens only once in a decade or two, or twice in a decade. This happens every night if you are at lower northern latitudes or southern latitudes. That's all I have, I think. I think I held you much longer than I tortured you a little bit, I guess. I have some interesting things, but yeah, that's mostly explaining. Yeah, that's my pictures from, I took the previous one as well. Those are unprocessed, I think. Then when I remember processing them. From Foothill College, just outside of the observatory. That's where the parking of the cars on the other side, outside of the. I found it was the best place to see it from the Bay Area. So I went to Stanford. I went to other places, tried to go up in the hills. No, I could get a lot of.
What time?
That was around 11:30, I think. Where is the night? It's outside of the Peninsula Astronomical Society Observatory, which is within Foothill College. Yeah, so it's right outside of the parking. Foothill College.
It's literally not even
Yeah.
10 minutes away.
10 minutes away. That was the best place because it had nice isolation from light posts and street lights and whatnot. So I could see that. I actually could see this pillar, this beam here, or this one. I remember I could see that with my eye. That I was, because I could definitely be happy that I was able to see it with my phone. Those are pictures. But once I was convincing myself that, oh, I can see that, I don't need my phone, then I was very happy. And that was the only place I could actually see it outside of the observatory. I think some people were inside the observatory, but probably missed missed that because they were not looking at the right location. But if you had gone outside, you could actually see it. So that's really a depiction of this magnetic field. That's my final slide. Those of you who are interested in looking at the data yourselves, you don't have to know computer languages or whatnot. You can go to this website. This is from our lab at Lockheed Martin. In particular, we have this tool that you can really go and you can check how the sun looked like over the last 24 hours or something like that. And you can play your own movies, you can zoom in, you can zoom out, you can use an iPad, you use your fingers to zoom in, zoom out, or you can use a mouse pointer, whatever, and do your own stuff. Or you can overlay different wavelengths, and you can flick through them, or you can smoothly transition from one wavelength to another if you really want to look at the details of how different wavelengths look like. But the important thing is, when you hear on the news, there was an explosion on the sun, and you don't have to wait for the news station to show you a movie. You can just go to this webpage and you can play the movie for yourself. That's the one thing.
So is that from an image from a satellite watching the Earth?
Correct. And it's assimilated every day. We provided last 24 hours or even more, 48 hours. But we also provide data that are actually archival data. You can go to browse data here. Well, you can explore it on your own time, but you can click on browse data. You can find extremely impulsive, explosive events on the sun, and you can play the movies for yourself, even if it happened a while ago. This mission has been operating since 2010, continually. Every second takes a new picture of the sun at different wavelengths, cycles through all the wavelengths every 12 seconds. So every minute we get 5 batches of these wavelengths, and it has been operating since 2010. So now we're at 800 million images acquired since 2010, and it keeps working. So yeah, we're happy, we're proud of this. That's it from me. If there are any other questions or clarifications, I have additional slides. So up to you.
Thank
Yes.
you so much. It's okay to have questions, but I do want to remind everybody, they will close at 9.
Right.
And so 5 minutes before then, we shut it down.
Sounds good.
I am going to remind everybody the Foothill Observatory is open, and that's like some of the images we can see. Details, go check it out Saturday mornings.
That's right. That's right.
10 and 12?
10 and 12, yeah. So if you have questions, we will try and address them as quickly as
Right,
possible.
right.
I saw your hand, Marcel.
It's like,
Yeah.
after these explosions,
Yeah.
have they noticed over time, the next explosions tend to be near the original, much further, what's the pattern?
So when there is an explosion on the sun, is it that one region might produce another explosion, and actually that means there is more likelihood to make predictions based on that? The answer is yes. However, when we're looking at small explosions, the answer is no. They can happen anywhere. But the big ones, when you see a certain area where you have very ugly looking sunspots on the sun, you know this is going to
The
blow.
ones that concern us.
Yeah, and you know it's not going to be just one, at least from experience. You actually see them having recurrence of such activity. So that's what happened back in 2024, that aurora image that I showed you. That same region produced 10 different explosions within 3 days. It's really immense. Usually you have one at a point, that's it, if anything. Yeah. Yeah.
So, the different websites that give forecasts of stuff, they all work off the same data, basically?
Exactly. So our lab has built this instrument. Everybody uses data, including the Weather Service. The Space Weather Prediction Center is called. They are paid by taxpayer money. It's part of the government, and they are tasked to make predictions about explosive events. So they use data from our satellite. We also have built a satellite dedicated for that purpose. It's called SUVI. SUVI, Solar Ultraviolet Imager. Same data are available through the same webpage.
And so do they actually observe particles coming to the Earth, or they just look at the sun's explosions and they know how long it takes?
Those are two different things. One is they want to understand the likelihood of whether one region might produce explosions. to make some rudimentary prediction, which is actually the most valuable thing. Once an explosion happens, maybe it's too late for most of it. The other thing they try to do is what you just said, whether they can actually track the time of arrival, can predict the time of arrival. That's very difficult to do. Very difficult to do. It's so difficult that statistical analysis shows that you can only get an answer within plus minus 16 hours. That's our current capability. It's pretty much, you have to tell the astronaut stay for 30 hours in the shelter,
I know.
but that's not going to help.
Weather predictions are better than that.
Exactly. Yeah.
Thank you very much.
You're welcome.
Thank you.
Thank you for the very interesting questions. Thank you. Thank you.
Canadian, do they have any trips on the